Welcome to Stop Stitching Database Together, Vector Search meets Feature Store. I'm Guilherme Nogueira, Technical Director at Scylla. And essentially, Tim and I, a colleague of mine, will be covering essentially collapsing vector search as well as a feature store on a single database for high performance, high throughput, low latency workloads running at scale. So a little bit of introduction first. I'm Guilherme Nogueira, Technical Director, and essentially I worked as a solutions architect here at Scylla for roughly 3 years. And meanwhile, I had contact with plenty of industries and helped users be successful when running at scale with ScyllaDB. And with me, which will join us a little bit later on this presentation, is Tim Koopmans. He's a Senior Director at ScyllaDB, and essentially he has a history of building high-performance applications and training machine learning models, and he thinks that he can't get it right, but I kind of disagree with him. And he actually built his own Bloomberg terminal. So if you have any questions on that, please feel free to ask him too. So going over the agenda for today, first we'll cover what is ScyllaDB, what makes ScyllaDB so great, and why ScyllaDB fits your AI pipeline. Then Tim will cover his real-world application where he built a real-time AI pipeline to safely tackle high throughput writes for both features and vectors, as well as really low latency retrieval of features and vectors on the same data store. So it's going to be a nice story, and we hope you learn a lot from this session. Before we move forward, though, a quick poll. Where do your vector embeddings live today? We're assuming you are running, but do let us know if you're not running it. So is it on a dedicated vector DB, Pinecone, Milvus, or Quadrant? Maybe it's on pgvector if you're running Postgres or Elasticsearch, OpenSearch, Cassandra, MongoDB. Maybe you're embedding it in your own program, in your application through a library. That's also an interesting use case. Let us know if you're doing that. Or if you're using anything or any other combinations, do let us know on the chat. All right, so at this point, we expect you to be a bit familiar with Scylla, but just going over quickly over what is ScyllaDB. ScyllaDB is a database architectured with close to the metal design that is essentially aimed at delivering millions of operations a second per node, and to provide all of that with single-digit millisecond P99 latency. So you get fewer nodes running these massive workloads, less administration overhead while running a smaller cluster, and lower costs altogether. And at this point, you might be asking yourself, why ScyllaDB? So you already know what, but why? And we'd like to mention some ScyllaDB users that leverage ScyllaDB for various use cases, most especially real-time AI at scale, which is what we're covering here today. From feature stores, leverage ScyllaDB by TripAdvisor to provide highly personalized recommendations for billions of monthly users, to targeted ad online by the gaming company Electronic Arts. Essentially, they run this ad platform on top of ScyllaDB, offering their millions of users. And Sprig, which is a user research platform that leverages ScyllaDB for its AI-centric customer research platform. And if you'd like to learn more about the use cases, do check our website, and we have plenty of great stories from those users telling how they leverage ScyllaDB. Now, I told that ScyllaDB is designed for modern architecture, but what does that mean exactly? ScyllaDB runs one shard or thread per CPU core with an isolated memory and asynchronous I/O. Essentially, this shared nothing architecture will help eliminate locking because there's no cross-CPU communication happening, providing linear scalability as you add more resources or nodes to your cluster. Then it also leverages user space schedulers that adjust I/O and CPU dispatch to maximize hardware utilization. This will essentially prevent background tasks, which need to be there so the database can function, from starving latency-sensitive queries coming from the user workload. ScyllaDB also has a really nice built-in cache that caches hot data directly in the memory of the CPU core that runs ScyllaDB. it self-tunes itself based on access patterns, so it will know exactly which rows to prioritize according to the recency of hits on that row, and also balance the memory pressure, so it always keeps a maximum data in memory without affecting the performance of the cluster in general. And it actually helps keeps workloads fast as the workload changes. And then with tablets, we essentially partition data into small chunks that dynamically rebalance across the cluster. And this helps ScyllaDB to provide elastic scaling, helping you handle peaks of operations with lower infrastructure costs because ScyllaDB can scale just so fast to tackle those different workload targets. Last but not least, ScyllaDB lets you control how your workloads compete for system resources. By leveraging the user space schedulers that I mentioned earlier, essentially this ensures latency-sensitive queries are fast, and even with other heavy workloads running on the same cluster, such as analytics or even vector workloads on the same infrastructure. Now, Tim, I'm pretty sure that our audience is really eager to learn more about the application that you built for today's presentation. So I'd like to call Tim on stage so he can present the aspects of his workload that he built and prepared for the presentation today. Hey, Tim.
Hey Guy, how's it going, mate?
Great, great. How about you?
Yeah, just checking everything's working for me. That's thanks for the intro. Yes, I think we can assume I'm assuming that people have seen the first webinar where we built a feature store. So we're going to build on that in this real world application and add vector search to it. So if you haven't seen the first webinar, I'd encourage you to see that because that lays a lot of the groundwork and you probably see how this application's evolved. But to just sort of quickly recap, as Guy alluded to, I have like deep interest in financial trading and algorithmic trading. And one of those things, that I obviously look at, one of the assets is cryptocurrency. And Hyperliquid is a really big decentralized financial exchange or a DeFi exchange that runs lots of cryptocurrency, perpetual trading, futures, all that sort of stuff. And so basically, with Hyperliquid, in this particular application, what we're doing is we're drinking from the fire hose where every trade that happens on the tape is going to get filled on this particular exchange. And it's something like 5 million fills per day. You know, it can vary in terms of the throughput, like it can be around 60 to up to 1,000 fills per second, which doesn't sound like a big number, but when you start to write features, that obviously will amplify that sort of write volume and a reasonable sort of growth in storage as well. It's around 100 gigabytes per day if you are ingesting this data source. And in the last webinar, what we did was we actually built a feature store. We showed you how you could get, per coin and per wallet features, and some of the features. I forget how many features exactly, but it was, it was dozens. It wasn't hundreds of thousands, but that, like once again, that can also grow and amplify. Something like 100,000 writes per second was what we achieved in the feature store last time. And we also had that desirable sort of single digit P99 latency as well. So they are the attributes, and they continue to be our high level requirements for this particular application. Now, the nature of that workload, just to reiterate, is it's very bursty in the sense that you're going to get spikes through things like flash sales, promotions, news, etc. They're all going to contribute to this really bursty 24/7 workload. So it's pretty hard to predict what the volume is going to be. You just have to be able to absorb it and hopefully you don't fall behind. It's highly skewed in the sense that the traffic, the data distribution is not normal. You have popular tokens like BTC, Ethereum, for example, they're going to dominate. So you're going to get very long tails where you barely trade, and some are going to have huge spikes. So that implies things like hot petitions that you have to be mindful of when you're designing your schema. And once again, we went through a lot of those sort of considerations in the last webinar. And the other nice attribute actually is that it's very high cardinality because we have millions of wallets We have hundreds of coins. So that gives us something sort of concrete to work with in designing our petitions and our clustering and how that works across the schema or across the data model. Okay, so that was the lightning version of the last webinar.
Yeah,
Now, now we want to do something more interesting because if you follow the tape, and I should highlight here, Guy, like I still have a full-time job, so obviously my algorithmic trading isn't that successful, and anything that I say here is definitely not financial advice, and in fact, I'd advise you not to follow it or try any of the things that I'm doing. But it does offer a good context for building an AI pipeline because this is realistically what a lot of trading desks are doing, this type of work, except on a much bigger volume. So it's super interesting to me, and hopefully yeah, you're going to learn some tricks along the way. But one of the things that we want to do is build similarity between features. So in the last webinar, we were building features. Now we want to start to look at how those features are related to each other. And by related, I'm not talking about doing a where clause, joining tables or anything. Like we're not a relational database. And in fact, we're after
good to
something.
know.
Yeah, yeah, we're definitely not that. But we are interested in things like, we want to be able to copy the smart money, for example. So we want to be able to find wallets that potentially behave like other profitable wallets because they could be like a leading indicator that something is, maybe there's some insider knowledge there that we can tag along with. We also want to be able to identify things like coordinated activities. So we want to be able to find clusters of wallets that have near identical behavior. So in financial terms, they could be involved in more fraudulent things. Maybe they're doing wash trading. Maybe there's signals for us to avoid those particular trades or those particular market conditions. And we're also interested in per market behavior. So we're interested in who is trading, particular assets or particular coins in the same way that our own simulated trading desk wants to perform. So that's the reason for adding vector search into this particular pipeline.
I'd like to just comment that it really mimics the pipeline of fraud detection, analytics, pipelines. So it is really great that we're covering those three aspects because it gives people a lot of ideas on how to leverage the vector store in order to achieve those goals. So really
Yeah,
cool.
exactly. It's like it's feature store. Now what? Like you want
Yeah.
to do, you want to do more with that information and potentially train models,
And
etc.
which
So
businesses don't want fraud detection, right? So everyone
yeah.
can learn a bit from it.
Yeah, it's super interesting. It's a super interesting topic. I think
Definitely.
yeah, especially when you're using real money, you obviously want to be aware of sort of this type of behavior as well. So yeah, this slide really builds on I think what Guy was saying. It's the same database here. It's just we're adding one more column, and the first thing that we're doing is we're going to alter our table. We had the wallet features table in the last webinar, and we added one more column to that table that already holds all those features. And like I said, it's not a new table. It's not even a new key space. It's not a new store or anything. All I'm doing is adding a vector of 16 floats, and that will be. I'll talk a bit more about what that means. But these 16 floats in general are going to hold things like profit and loss and the field count, the same sort of information that the features were derived from. And then the second thing that we're going to add to the schema is we're going to create a custom index. Now, there are a whole bunch of really great university labs on our site that you can follow. You can do a lot of this stuff in Docker containers and just to learn the process. We're actually going to drive it through with some load so that you can see how it performs. And this is a ScyllaDB feature. It's not really an extension or anything that you bolt on. You'll recognize some of these things, the similarity function I'm using cosine, because all of our dimensions have been squashed and from different scales. So if you can think of, if you're talking about financial things, maybe we have things in the billions of dollars and hundreds of thousands of dollars. We can use log scale to just compress that into, a value between 0 and 1, and we can start to care about the shape of the behavior and not the magnitude. And I'll explain what I mean by that, but that relates to, in particular, to the cosine similarity function. And then the third thing that we'll be doing is just selecting. And once again, this is just plain CQL. We've got an order by embedding. So we've got the ANN off. So this is the approximate nearest neighbor. And it's a question mark with a limit 10. So that question mark is just the bind marker. You've seen us use that with prepared statements. Obviously, we want to make this run fast. And because it's a prepared statement, exactly like the point reads that we are doing, it's going to be the same session, the same driver, the same connection pool, everything's the same. I'll talk more about what that limit 10 means as well shortly, because that has some significance in terms of ANN.
Just before we move
Yeah.
forward, Tim, I'd like to mention that here you use the vector of just 16 floats. And this is all because first, Tim was able to just essentially compress that data into 16 vectors or embeddings. But usually in production, you would see hundreds at least of vectors starting from 384, for instance, if you're working with large language models. So this, as this is a lab, this is just for demonstration, even to allow the audience to replicate the exercise in their own code. We pick this lower number just for ease of managing it.
Yeah, and it's actually it's I'm glad you said that, Guy, because I think when what people get thrown off by when they start talking about things like vector search and ANN is that the dimensionality, which is what we're talking about here, the 16 dimensions for this example versus maybe 768 dimensions for a standard text LLM encoding. A lot of the time, a lot of the examples that you see out there are about chatbots and LLMs and encoding text and using like a model to generate the embeddings. But you don't have to do that. And you can create and I think maybe I've got a slide on this. I'll get to it. I'm sure I will. But and a vector is just an ordered list of numbers. That's it. And it can be just one, it can be two, it'd be two-dimensional, it'd be three-dimensional, it can be 16, thinking in the 16th dimension. Can't really think like that. And it goes all the way up to 768 or even thousands of dimensions. It doesn't really matter. The maths holds all the way through in terms of the similarity functions and the way that works. Don't ask me to explain it. I know Pythagoras, and that's about the limit. But yeah, it will. The math is true enough no matter how many dimensions you throw at it. And ScyllaDB, of course, is we do a lot of testing around that different dimensionality. So some of the benchmarks that you'll see, of course, around vector search will be based on higher order of dimensions and different concurrencies. So that different limit value of k, for example. But yeah, thanks for bringing that up.
Sure.
Yeah, I think the other thing that you'll see in some of the other basic presentations about ScyllaDB and vector search is I just want to sort of peek under the hood because I don't want you to sort of leave from this webinar with the wrong picture. The index that's served by ScyllaDB's vector store, it's a separate process. It's written in Rust, and it holds that HNSW graph entirely in memory. And it's fed from the base table that we're writing the features to. It's fed by a process called CDC, or what do we call it? Change data capture.
Change data capture. Yeah.
Yeah. So it's technically another moving part in the ScyllaDB landscape, but it's all abstracted from you. What it isn't, it's not another database. So it's not something that you need to go and deploy. You don't need to provision it separately. You don't need to figure out connections between things. You don't need to write a single line of synchronization code. And probably the most important part for me, and this is a blessing for anyone that's like doing this at scale. There's no ETL, extra ETL in your application. So I'm just writing my features. We've collapsed all of that operational surface into something much, much less complex. And that's a real win for anyone that's doing this at scale, because we'll talk about some of the considerations later, but synchronization lag is a big thing in terms of handling data moving between different data stores. So that's a huge win. Do you want to add anything to that, Guy?
Yeah, just removing pieces that synchronize data for sure reduces the surface of possible issues, right? So there are less point of failures if you don't have Kafka in the way, for instance, just to synchronize data from a CDC table into your vector search. So here we're exposing how it's done, but you don't have to worry about it because the service itself handles it for you.
Yeah, and I'll probably just show you once we start showing the cloud cluster and stuff, we'll show you where that's all configured as well. I think I've got a
Yeah,
couple more slides of just a bit more theory. Not so much theory, but just so it's really concrete in your mind. What is a vector embedding? Um, if your mental model is it's just some opaque thing that a model emits that you have to just take on faith value, then or face value, it's basically opposite that. And so what I've done in this case, and like Gear was saying, is I've created 16 dimensions that track a wallet's trading behavior, roughly like 5 groups in here. But the things that I'm interested in is, how did that person trade? Are they directional? Do they work both sides of the spread? How much of the volume is passive, for example? How big they are? Like, what's their trade size? Are they whale scale? Are they little minnows in the pond? What are they trading? Are they just like trading one coin? Are they trading 50 assets? And how concentrated is the volume around those assets? And how well is it going for that particular wallet, that the particular trader? Is it, let's look at their realized profit and loss. Let's look at some of the archetypes that we sort of assigned to them back in the first webinar. And also of interest normally is like, when are they trading as well? So even though it's a 24/7 sort of behavior, you'll find that a lot of trades happen within certain time buckets. So I think I've got like, four buckets there throughout the day. So every single one of those is a feature that we've already seen in the feature store. I haven't invented a new pipeline here to produce them. All I'm doing is I'm taking the features that we already computed and then just write them down in that fixed order, that vector of 16 floats. And if you look at that wallet at the bottom here, you can probably see, that someone taking inside. They've got some directionality. They're not making a market. They've got zero on the maker share, and they're always the aggressor, and they're always crossing the spread. They've got I think there's a 1.0 there. Yeah, 1.0 on the top coin. So they're sharing one coin and that's it. They got flat profit and loss. And then the hours that they're trading is like between 600 to 1800 UTC. So that's how we can sort of categorize, like, if you like, or describe the behavior of a single wallet. And we have one vector. Once we have one vector, we can calculate more vectors for all of the wallets. And I think I've got close to 1 million of these vectors. And then once we have that vector in that 16-dimensional space, we can calculate the angle, the cosine angle. And obviously, the closer things are aligned, the more they're in the same direction, you'll get a value of, say, 1. If they're at like 90 degrees to each other, it means that they have no relationship at all. So that would be a scale of 0. And if they were completely opposite of each other, which is going to be rare in this use case, but maybe it's relevant in other use cases like fraud detection, then they'd have a score of -1. So we'll see all of our scores between 0 and 1. And then I've actually got a function in there that just recalculates, like gets the angle back so that we can describe what that similarity was like in degrees. But yeah, if you navigate through that 16-dimensional space, which obviously we can't draw that, but that's kind of like what it looks like here on the right-hand side. So we're finding, 4 hops in the neighborhood of like 981,000 comparisons. And that similarity is found within microseconds. So that's the really important part here. If you tried to do that with 16 columns, with a where clause and a relational database, it's just not going to happen
yeah,
in any good amount of time. So that's the real power. And then we can start to see where these clusters of wallets and how they're behaving. So it's super interesting. I don't want to nerd too much out about this. I find it really interesting, but one of the things about cosine is it takes away the amplitude. So it doesn't say, if something is handy or if it's really, really, really handy is, like if you're comparing those two terms, you can't measure that sort of the amplitude of that because cosine strips that away. If you're interested in amplitude, you might use things like Euclidean distance, for example, which is measuring the distance between the points in that space, which sort of angle is implied because if things are pointing in the same direction, they're still kind of the same. But if things are, it gives you a
pulling
different
apart.
picture. Yeah.
Exactly.
So yeah, it's brain bending stuff, but it's good to know just the basics of how this stuff works when you're implementing it. Okay. And then what have we got here? We want to run it live. So um, I hopefully it's running live. Let's have a quick peek. We are going to, where's my, there we go. So it is still running live, which is great. My demo hasn't crashed. Probably see here, I think we're running about 67,000 on the input in terms of the fire hose. We've got a P99 of around 4.5 milliseconds, which means our feature freshness, if you remember from the last time, when we take the delta between the read and the write, is hovering. Well, you can see that live value here, but once again, it's single digit millisecond in terms of freshness. We're also running index queries on the vector search store. So I've added this panel here. If you can, hopefully you can see my mouse moving around.
Yep.
Yeah. And the yellow line is actually the index build rate. So I've actually switched off the index building because I want to show you like the perfect, I'll show you the quiet state of a feature store with vector search. That is, we're not rebuilding the index as we go. And yeah, we have quite favorable conditions here. I think we've got around 3,500 queries per second. So that's I'm talking about not operations per second now. I'm talking about ANN queries. So we're doing about 3,500 of those per second. We are returning nearest neighbors of K. So concurrency of K is 10 for this. And obviously you can experiment depending on what you need, but I'm only trying to find 10 wallets or their nearest neighbors.
Mhm.
And none of them coming back with empty results. And I'll also talk a little bit later why, why we want to do that or why that's important. What else do I want to say? Everything else is the same from the last webinar. This is all just the feature store performance. So that's what's happening at this point in time. But when you start to think about like, okay, so we've got this information I'm indexing, I've got some pretty spark lines, but what do I actually want to do? Maybe I want to start to go crazy with a node edge graph. But this can run queries in real time and start to find, wallets. Now I've forgotten. Yeah. So if the ring is tight, I think that's the wash trade from memory, looking at stuff like this. And then we can look at like smart money, looking at total profit and loss. So their profit and loss is like negative, so that they're all trading particularly poorly. These guys are in the positive. And so I can look at this wallet and then I can find other wallets that based on those 16 dimensions are doing the same thing. Maybe they're achieving like in terms of like, so the similarity is based on what I was talking about before, the 16 dimensions. Obviously, their profit and loss is all different, but they're all positive. And so hopefully you can start to see here how you could apply this. I'm not going to take this further in terms of this demo. Like I'm not going to go and create a trading algorithm for you. I'm sure Guy might be interested by the sounds of it, but you can
Yeah.
start to see how we can use this information in the generation of other signals. Maybe we generate new features from this data and then rewrite that back into our feature store. And then maybe we're doing things like training on top of that to, some predictive analysis based on this type of behavior over time. So yeah, that's the demo part. Let me just go back to I think that's what we wanted to show. Do you have any
Yeah.
questions on the
One
dashboard though?
last thing here, yeah, before we switch over to the monitoring, is we see the AAN latency essentially at the bottom of the similar wallets panel, right? And it's fluctuating because it's just a demo, but it's really within single digits millisecond latency. So this is pretty great for this volume of queries at that rate.
Yeah, and I'm actually measuring. So it's funny you say that because this is 2 milliseconds, still great. The actual this is measuring it from my client, which is an overloaded client. So I'm breaking all the rules here. I'm running like the loader and the client and everything off a single box. It was the same. It's a big box. I think it's like 24 cores or 48 hyper-threaded cores. But yeah, even on a overloaded Python driver here, it's yeah, it's pretty good performance.
Yeah, it's
Um,
even more surprising. Yeah, because Python is known for its higher overhead in performance. So if you can get this from Python, for sure, if you
mhm.
used other more performance languages and then scaled according to reads and writers, that would make much more sense in terms of
Yeah,
performance.
yeah. So yeah, hopefully, you can if you're looking for this particular demo, you can we've got the link shared on the screen. You can go. I've actually done this as a PR. Sorry, I'm getting all these notifications. Hopefully, I'm not recording all those. But
Nope.
yeah, we've got um, all of this is sitting in a PR, so you can see all the stuff that I've changed since the last webinar. You can run this stuff for yourself. It does run in Docker if you just want to run it locally. But I am using like probably the interesting one would be this. This is where I'm showing you the dimensions and how I'm calculating the vectors for those dimensions. It's very simple math. Like I said, it's not using any model to generate the vectors. So that's a difference here. But that's just a different way of doing it and an equally valid way of doing it. You can see all of that here.
Yeah,
But
absolutely.
yeah, the other thing I'll probably, before we jump into the monitoring, because I think that's our next slide coming up, but we could probably just quickly talk. Do you want to run through here how we got vector search? I can point and click for you.
Yeah,
Um,
absolutely. So what did we do here to prepare for the webinar? First, we deployed a cluster. We VPC peer to your client. And after this is done, essentially we were using a single AZ, so a single region and a single AZ. This is just to save costs. Of course, not a production recommendation at all. But we selected a single AZ. And once the cluster was ready, if you can click on the three dots on the top right, Tim,
yep.
it's pretty easy. Just there's an enable vector search. It's not there because it's already enabled, but you
Oh,
enable it.
yeah.
If you go to resize, it gives you
Yep.
the same option. So you can click on it. So here you have options to pick to choose from how many nodes you want in terms of how many replicas you want across AZs, as well as the machine instance type that's going to be used to deploy on those nodes. But if you don't have an idea on the number, you can use the Get Instance Recommendation button, which is a calculator that helps you pick through based on the number of dimensions, the number of vectors you want to embed onto the system. So it really helps you in terms of planning for that if you have nowhere to start. Really self-service way. And of course, you can tune the target QPS, the recall target, the K number. Essentially, it gives you all the variables that you can play with in order to estimate what a cluster would look like.
Yeah, it's fantastic. And yeah, hopefully we've explained all of these values accidentally in this webinar, but I think we've covered them all. Definitely covered number of vectors, dimensions. We've spoken about queries. Yeah, this is awesome. We
Yeah,
didn't really
we didn't
speak
talk
about
about,
recall targets, but yeah, that's
yeah,
also a factor that is going to obviously impact performance and sizing. But yeah, we've covered K and yeah,
we
I
didn't
think
cover quantization, which is we
yeah,
usually store those vectors as 32-bit floats in memory. So they all will take that amount of memory in order to be stored. But if you want to store more data, you can quantize it, which is essentially to use abbreviated integers that data types, sorry, that would help store more data on the same memory size. So here, if you go to uint8, you can store roughly 3x more data. And if you go 1 bit, then you can store 10x more
yeah,
data. So it's basically depending on what the workload looks like. There are some caveats to each one of them. So that's why there's a documentation link on the previous page. But then you can increase recall rate and still be very efficient in reading that data.
yeah. So this is the documentation that I think
Exactly. Thank
yeah,
you.
yeah. So yeah, definitely worth having a look at the guides, having a look at the labs, having a look at the cost calculators. But you know, at the end of the day, Guy, nothing beats just running
I
the target
totally
load,
agree.
right?
Yeah.
So this is what I've been. This is the demo. It's still running live. Just to make sure I'm not telling any lies, we can probably go and just refresh this screen. Um, there we go. We've got live writes coming into the feature store, 28% utilization. We've also got a pretty healthy amount of reads happening as well. Our P99 latencies, you know, obviously the reads are super low. Our write latency P99 is a what 2.91 milliseconds. So that's the
Yep.
whole that's at the whole cluster. But yeah, I guess my point is that we also have, like, if you go to the hamburger menu, you can get to the vector search Grafana dashboard, which is what this guy is. And yeah, my point, Guy, is like just run it with your load, put your application, hook it up. It's very low surface area is very small in terms of what you need to change to get this running, and get some real stats. You'll find out what your bottleneck is. Like clearly, I have bucket loads of disk at this particular volume, but the memory footprint for me is quite low. 16 dimensions, a bunch of floats. It easily fits into the memory that's on this cluster.
Yep.
I would say
Yeah.
my limitation is probably CPU. Yeah.
Yeah, essentially you're storing roughly 1 million vectors for the wallet coin mapping.
Yeah.
So of course there's not a lot, but you could certainly ingest much more data here and still be very efficient in reading it back. As you demonstrated on the previous screen, you're still writing to the database. So the index is being live updated. Scilla is generating the CDC records, the vector search
Oh,
service is
actually,
reading.
I'll correct you there again because I put a special feature on to disable that. You'll see here my index build rate is 0 at the moment. So what I
Oh,
wanted to
cool.
do, I didn't tell you about that. So that's my surprise. But I want to give you, like, I want to see what it's like with a quiet index, because like I think a lot of people just, you know, mask the fact that things are happening. Like I've got a few slides on this anyway. We'll talk more, but there are different ways, there are different times that you need to write, maybe maintain your index as well. This is a really good point, because this is definitely going to add load and add, increase my tail latency. But right now, the best case scenario, like we're talking, you know, microseconds, right? For the P99,
Absolutely.
it's really fast. That client milliseconds that you saw is just the client overhead, the network hop and running a fairly congested loader.
Yeah, and just to remind everyone that that's still a production-ready deployment, because even though it's running on a single AZ, it's still going through different VPC peerings and whatnot in order to reach the ScyllaDB cluster. So there is
Mm.
some network overhead there as well.
So what I did is, and here's my surprise. I've got a magic switch that can just like turn my writes on and off.
Ah,
And
cool.
so now we are going to be indexing, re-indexing from that fire hose, and there's definitely some performance considerations here that I want to talk through. I'll just let that fire up a bit, because you can see here it's now, the yellow line here is my rate. It hasn't updated the build rate here. I'm not sure if that's just a bug in my thing. But if I go back to the monitoring here, I'm hoping, yeah. So now we can start to see, the records are coming in, and definitely going to see an impact to, P99 latency, as we've just opened the floodgates there. CPU is increased. This is definitely having an impact on the vector store, and I've got some reasons for this as well, which I'll elaborate. But do you want to? The other thing that I want to show you guys, which was a bit of a surprise, not so much as a surprise, but when I was originally looking at the dashboard, in terms of this guy, I was like, why is if I go back to, like, I think if I look at it like per DC, I was like, I had rather large write volumes, right? And so there is like the cost of replication across the three nodes that's included. But if we just look at it via the index, what I was seeing was like, sometimes I was seeing like a higher write volume overall, at, say, like the instance level or the cluster level. I was like, what's going on there? And then I realized this. There's also CDC
Yeah.
happening. So,
Yeah, those include the internal writes that happens within the database.
mm.
So
so
if for
so
each write that you include, it will also mirror on a row on the CDC record table, virtual table, that
yeah,
will then allow the vector search to function.
yeah. So these are all important considerations, and this really accentuates the need for you to benchmark your particular requirements preferably on the cloud. It's really easy to get up and running, as we've hopefully shown you. Just modify your table, point and click and go. But it's really important to get an understanding what your footprint looks like because everyone's going to have different characteristics. And I can tell you, I'm making some mistakes here, and I don't know if Guy knows what these mistakes are yet. But this is just in me sort of going through this code earlier, and I was like, yeah, I think I'm doing some things incorrectly here, and I think I'll use that as a good segue if I get back to let's try and get back to the webinar, say. So we have been talking about tuning the pipeline. Do I have a slide? So I've obviously shown you Grafana and some of the different dashboards that we want to look at. Was there anything else that we need to look at in terms of the dashboards, or would you say that's obviously the good old detailed view? You know, we also want to look at the shard view. That's really important. We've still got
Yeah,
some
that's the highest
imbalance.
granularity that we can go. And you can look at the by instance level, by shard level, as we have here, or by DC level as well, if you have multiple regions or multiple data centers. But what I would like to see is go back to the vector
Mhm.
dashboards and look at the instance level to see if the workload is balanced across instances
So
that
by
we have.
node, yeah,
Yep, exactly.
yeah.
Okay, so we have very few data points, but we can see that yes, the floodgates really did, um, you know, create a lot of back pressure on the system.
Mm.
Scylla is going through all those records that are trickling in into the system, all at very short period. And of course, the client is still pushing more data, right? So
Yeah.
you see requests decreased because if you see index request rates, it came down from 2,500 a second to just 500. So that's not only the system has higher latency, but also the client has stopped pushing that many operations because the single client it's bottlenecked.
Yeah,
So
yeah,
there's a lot
absolutely.
going in just a single state there.
Yeah, and you saw that in the last webinar, and we spoke about the performance considerations, running everything from the same box. Generally, a bad idea. You don't want to do that in real life. You would want to start to split out the different components of your pipeline onto appropriately sized hardware as well. Um, we also spoke about, you could rewrite some of those components, like not use Python perhaps, and maybe use Rust if you wanted to squeeze more throughput for a given hardware profile. Although you can, I've done all of this in Python, and my preference is to do as much of it in Python as possible because definitely in the machine learning space, and I guess the wider sort of AI space, like Python seems to be like the standard for me. But yeah, the other thing that you touched on there, the CPU has ground up. I think we went from like 40s up to 73 on the vector store. And one of the things that's happening that I realized is that I'm just sending the whole fire hose over to the vector store. So I'm not I'm not filtering. Like I could definitely filter. Like I don't need to send everything over via CDC. Like all features being written for then for via CDC for then the vector store just filter out back out again because they're like I don't need all that extra information. So that would definitely have an impact on performance here.
Yeah,
But
if you're writing data needlessly, that data still needs to be transferred and indexed and searched when you query it. So
yeah,
if there are edge cases that you can eliminate, of course, that helps on query time.
yeah, yeah, exactly. And yeah, there's anything like the other lessons here are like just that generally there is some imbalance. I think we had some petitions that were imbalanced in terms of data that I didn't address either. And that's like I said, the nature of the data that we're processing as well. But overall, I'm pretty happy with that. Let me get back to the slides and talk about this one. All right. So I guess the big question in my mind is freshness under load. What's the point of having all of these feature store, etc., if you're serving up stale features? And I've said in other webinars, if you serve up stale features and you're training you train models on historical data, and then the historical data expects the features to be accurate up to T0, and then you go run inference on that on the feature store in production and you feed it back into the trained model and run predictions, and now your features are lagging, T-1 or T-2 or whatever it is, your unit of time, then obviously you're going to have problems because now the model that it was trained is making predictions on stale data. So feature freshness is like a huge component here, equally applicable to vector search. And like I said, this is like an iterative thing. It doesn't mean like we just stop at vector search and then that's it, problem solved, we've got our solution. Like it's likely that we're going to use vector search to generate features to feed back into the feature store to generate new features to train new models to then go back and rescore old models, etc. So it's a complicated beast. I'm only doing hobby stuff and mine's ridiculously complex. I can only imagine things like recommendations engines like TripAdvisor or fraud detection, the amount of passes that you have to go through in terms of iterating through the data. So feature freshness or freshness underload is a big consideration. So the key things here, we're still using blind upserts. So no reads before writes. The feature write is just one round trip, and you're never waiting on a read. We're using prepared statements, of course, passing them once, so the coordinator doesn't have to repass that SQL statement, 100,000 times a second. CDC, propagating to that index that we're building in real time. We just saw the impact of that. The embedding is writing in the same mutation as the features. So if you have one write, it produces one row image carrying that vector across for the vector store. The important part here is that CDC is doing that work for us. So once again, there's no ETL job, there's no scheduler, there's nothing to fall behind. And like Guy mentioned, live updates, generally we're going to be wanting that index to be modified in near real time or as it's being queried. They're not really separate phases, but once again, it's going to depend on how you're using that information. And I guess the last thing is that all of this is not free. There are physical constraints to how fast you can do a lot of this stuff. So,
Yeah.
yeah,
Yeah.
but yeah,
And I think that the highlight of all of this is as you struggle to keep the freshness in your system, if you're using separate systems to keep the feature store data and the vector search data, you have another piece of infrastructure that you need to monitor and ensure the performance 24/7. And ScyllaDB's solution essentially eliminates this middleman of ETLing or just transferring the data down into your vector store, which is a very, unfortunately, common design that you see in the industry.
yeah,
And we didn't talk about the freshness itself, but the P50 for freshness is just under 1 second. So as you write data into Scylla and Scylla replicates data to CDC, vector search is essentially loop querying the base CDC table and picking up the latest records as soon as it can and implementing that and reflecting that into the memory of vector search and allow you to query it. So it's very rare that you see such a tight, closed loop of writing features to the base table and that being reflected on the vector search store.
yeah, absolutely. And I think what's my next one? Yeah, performance considerations. If I was to take all of this information, and this might be good fodder for our next webinar, Guy, where we talk about costs, because we're talking about throughput and latency at the moment. We're talking about the infrastructure required, CPU burn, loaders, and choice of programming languages, etc. All of this is going to have an impact on cost. So I'll mental note, we'll keep that. But I think what I've learned personally, just going through this demo and building this demo for you with real xCloud, real data from Hyperliquid from the exchange, is that when you start to think about these embedding updates, a continuous slow trickle of embedding updates is definitely going to impact your P99. You're talking about the median. If we're just strictly observing P99, you're going to see that rise, and it's in exchange for very little freshness. Okay, so what I mean by that is if I have a latency service level objective that can tolerate some bounded staleness, then a periodic bulk refresh is probably going to be better than just trickling through the writes. Now, what that staleness looks like is different for every application. But I can tell you, I'm not building a high frequency trading system. I might be executing trades in 1 minute or 5 minute timeframes, for example. So I have a lot of leeway in terms of my ANN search. If I think about everything as a budget, and I start thinking about my data pipeline, I start thinking about the inference, I start thinking about, any vector search components, etc., maybe rescoring, feeding back in. I can start putting all those pieces together. And even still, like altogether, like even if we're talking like seconds, I'm still well within my slow of like a minute to make a decision on a trade. So once again, really depends on what you're trying to do. Everything is solvable with the right design, the right architecture, and the right sort of approach to around service levels. Um, yeah, the ANN under pressure, under right pressure, can also fail silently. We're not seeing that there, but that was, if you remember, I put in the app, I put like how many results are returned. And the reason I'm doing that is because um, don't just look at the P99 latency. There's no point just serving up zero records, basically. You want to see that you're actually returning information, and that's an important thing to monitor. Now, all of this stuff, maybe I should show you, is in the cluster. You can actually enable performance metrics, which is really handy. Now, I'm almost going to forget where it was. I think it's here. Yeah. So you can, when this is not enabled, I think there's like an enable Prometheus metrics. This is
Mhm.
super handy if you're building like live inference and you want to get access to, the information that's in Grafana over here. You can then obviously reconsume in your app, which is how I'm doing this sort of stuff. So get your hooks into that. Is definitely worthwhile having a look at. I'm not going to go through that. So it's probably a whole webinar on how to do
Yeah,
that.
a whole series.
Ask Claude. Claude will help you with that one. And the last thing, the other stuff that we've got, you've spoken. Oh, sorry. The second last thing is we don't want to put an index on a table absorbing those unrelated high volume writes. That's what I've done here. You're going to pay CDC amplification costs on every write, and the vector store is going to burn some CPU, just filtering out all the stuff that it doesn't need. So that's my mistake. Well, I want to leave it in there because I think it's a good learning point for this particular demo. And Guy, you spoke about quantization and rescoring. I think you added those points as well. So
Yeah,
uh,
yeah. Just to fit the performance considerations, not talking directly about your project, but in general, this is highly required for you if you have a large data set. So as you try to balance, performance cost and storing and accruing more data over time, for sure, definitely look into quantization and rescoring whenever you start to hit those thresholds.
absolutely. And like that's possible to do all in the same pipeline. So you don't have to think about doing that yourself necessarily within your own data. But everything varies because I find that I'm touching the data a lot in terms of normalizing things, scaling things, quantizing things. That might be already part of your pipeline as well. Um, yeah, I think we're at the end of the demo. I think we're almost out of time. We've shown that you can still maintain that same high write volume throughput with much less complexity. All I did was add a column and an index to the same schema. We have those same unified patterns, same CQL session. I'm not doing anything different in terms of how I'm retrieving the information. Um, We've spoken a lot about synchronization lag, and how the embedding can just ride the feature upsert, which is super cool. And that CDC really reduces that, or it helps us collapse all of that complexity and make it very simple to just add vector store into your pipeline. And once again, just achieving the thing that we're really well known for is predictable low latency, single digit P99 latency, under high volume, especially high write volume throughput, which is the common characteristics of many AI pipelines. One last poll, since we've been talking about it a bit. How fresh do your embeddings need to be? I'd be really interested to see what people's their real world use cases are. Is it real time in seconds or less? Is minutes fine? Are you doing hourly batches, daily batches? You don't know, you just haven't done this yet and you're interested, or anything else, let us know in chat or via the poll, and super interested to see what you're saying there. So yeah, I think that's all we have time for today. Thank you everybody for joining us. Thank you for the questions. Thank you, Guy, for helping me come up with this demo and getting it into shape. And yeah, I look forward to the next webinar where we will talk more about costs of these pipelines.
Excellent. Thank you all for the attendance, and thank you, Tim, for collaborating on it.